Okay, welcome again. Now we will add all those flux. Okay, so the flux, the total flux is going to equal to be phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5 plus phi 6. Okay, okay, so this is the phi 1 Vx. Okay, so let me just copy and paste it over there. So this is the first quantity, I mean the first flux of the first surface. Similarly we're gonna have this second surface. Okay, okay, the third surface. And we have this fourth surface. This fifth surface. And finally sixth surface. Right, so we will name it as let's say A, B and C. We will see all this A, B and C separately. So we have this A, right? Let's take it to once again. So what we can do with this? First of all, we can write Vx x plus delta x y cap minus z cap minus V of x y y cap z cap. Okay, so right, and we can take out this dy and dz as a common out. We can factor it out. Okay, now here we can, what we can do, we can just divide it by delta x and multiply over here with delta x, right? And when we take the limit delta x tends to 0, okay, so what happened that this difference and by divided by will gives the partial differentiation of Vx with respect to x, and we have these surviving terms. Okay, and yeah, and these terms is obviously okay, so and one thing that this delta x, delta y and delta z is actually the volume. Okay, so let's say a small volume delta v. So let's write it as a delta v for a moment. Obviously when x tends to 0, then volume will also shrink to 0, but let me write it for a while. Okay, so similarly for the B, equation B, we can also rewrite it we can also rewrite it. Let's factor it out. V of y x cap y plus delta y z cap minus V of y x cap y z cap delta x and delta z divide by delta y multiply with delta y. So that will give the partial derivative of V of y with respect to y times delta x delta, and of course okay, and let me correct it, times delta v, and of course delta v is the volume. Okay, so from the flux we are getting this volume term as well. Okay, let's take this C, equation C. So V of z x cap x bar y bar z plus delta z minus V of z x bar y bar z delta x delta y and divided by delta z multiply by delta z, and once again taking the limit delta z tends to 0. Okay, here we will also take the limit that I forget to mention over here. Limit delta y tends to 0. Only for the limiting case that quantity will becomes the partial derivative. Okay, so the total flux will become the A plus B plus C, all this summation of all these terms. So let me write it. Del v by del x d of volume del v y by del y d of volume plus del v by del z d of volume. Okay, so this is the flux. Okay, so this is the flux, that is or we can say the infinitesimal flux by y, because this volume element is obviously becomes an infinitesimal. So the flux that is coming out from this surface of that infinitesimal volume element will also called as the infinitesimal flux, right? So what next we can do, we can just common out this quantity d of volume, and obviously we can also this is Vz. Okay, I forgot to mention over here, this is Vz, right? Okay, so we can also write like this. Now it's look familiar, and we know what is it. V of x x cap, V of y y cap, V of z z cap d of volume, and obviously we can write it like divergence of this vector field V times d of y, and that will give the infinitesimal flux. Of course this is not y, I made a mistake. This is d of volume, this is d of volume, and taking the integral over both the side, of course we're gonna have this volume integral, this dy become d tau, which is the volume integral, and this become a dot dA, where a is the surface. So in this way we have proved this